Hello and welcome. In this video, we're going to look at parallel RLC branch currents. So parallel RLC branch currents can be a little bit tricky just because the final equation that we use, which is given here, flips our XL and XC from all other equations. And that's because of this diagram I populated up here. Usually we would see XL on top when we're talking about reactance and XC on bottom. And then our resistive value would be on this bottom horizontal axes here. Right, and in this case, we don't have that because we're talking about current. We have our IC on top. We got our capacitor on top, our IL on bottom. Our capacitor or our inductor is on bottom. Right, they're backwards, which means that these two are backwards here as well. Just keep in mind that anytime you're working with current, that this is the case for those, and that current is backwards in pretty much every equation that you're using in comparison. So we are going to use Ohm's law for this one. Basically, we're going to apply what we know about Ohm's law, voltage, current, and resistance, and our parallel circuit down here. In this case, we're searching for current. So we'll circle out our current equation. We know Ohm's law says current is equal to voltage over resistance. Since we're working with a parallel circuit, we know that this voltage comes down each branch. So we know the branch voltage. They all get 13 volts. 13 volts for each one. So we can use that, figure out all of our branch currents, and then plug that into our IT equation at the bottom here. So let's do that. We'll start off with our resistor. We'll say that our RIR is equal to voltage over resistance. We know that we've got 13 volts down that branch and that the resistance for our resistor is 180 ohms. We'll plug that into our calculator here. Say 13 divided by 180. That gives us a milliamp value, so we'll move that decimal point over 1, 2, 3 spots for 72.2 milliamps. So that's our first number. We can type that in here. 72.2 MA is already written for us, so we'll leave it there. Next, we can go after our inductor value and say that our IL requires another step here. It requires that we take our voltage source of 13 volts and divide it by our XL. Right? We need to have resistance if we're working with Ohm's law. You can't work with Ohm's law unless you have a resistance. So we can't plug in our millihenries value that they give us up here. We have to convert that. So first we're going to start with XL and say XL is equal to, that's our 2 pi equation. 2 pi, meaning that we're rotating around that circle. We'll multiply by our frequency, which is given at 12 kilohertz, so 12,000. And then we'll multiply by our millihenries value of 0.018 henries. I converted that out of millihenries right there so I don't mess up this final answer. So here we're going to say 2 pi times 2,000, or 12,000, multiplied by 0.018 for our henries value, and that's going to give us an XL value of 1,357 ohms. Right now we're in ohms, we can use Ohm's law. We'll plug in up here. We'll say that we started with 13 volts down that branch. Now we know that our resistance down that inductive branch is 1,357 ohms, and that will give us the current down that branch. So 13 divided by 1357. That gives us a milliamp value. We'll move that decimal point over by 3. We'll get 9.5. 0.58. And that's milliamps. That's our next number there. 9.58 milliamp. Right, our IC value does the same thing. We have to first figure out what we're doing with our capacitor, and then we'll apply that to our Ohm's law. So let's start off with our XC. We know that that's that 1 over 2 pi frequency of 12,000, so multiply by 12,000, multiplied by our capacitor value, which is quite small, 0.024 times 10 to the negative 6. And I'm going to plug it in just like that, so I make sure that I get all of those zeros in there. So 1 over 2 pi times 12,000 times a really small number, 0.024 times 10 to the -6 for our micro. That gives us 553. We'll round that up. So 553, that gives us ohms, which means we can plug into our Ohm's law equation for IC. So IC is equal to 13 volts down that branch, divided by 553 ohms for our capacitor. Set that out here. We'll say that we have 13 divided by 553. That gives us a milliamps. We'll move that over by 3 and we'll say 23.5 milliamps. So that gives us our third variable here, 23.5. Then we got one more to plug into down here. We have to figure out what our IT is, and they give us the equation for it. Again, watch out for the IC minus IL. We're working with current, so those two are flipped backwards here. And that's in the textbook, it's I total is equal to IC minus IL, but X total is equal to IL, or RL, be ZL in this case, XL minus XC. Right, so those are backwards. So just keep in mind that when you're working with current, that the totals are going to be backwards, and it's going to mess up your negative more than anything. Right, so let's plug in what we know I total is. We'll figure out this variable here, IC minus IL. We know both of those values. IC is 23.5, and we'll subtract IL, which is 9.58, 13.92. So we know that the I total for that section is 13.92 milliamps. We can plug in for the total current IT in rectangular form. And we know our IR is 72.2 milliamps. And that is a plus J for the back half here of 13.92 milliamps. And so now we just need to convert this over to polar form from rectangular form. That's our square root equation. We'll apply that here, and that'll be our final answer for this one. So the square root of 72.2 milliamps squared plus 13.92 milliamps squared. And that will give us our magnitude for the current in polar form. Square root of 72.2 squared. This will be output in milliamps also because I'm not applying my milliamps, right? So 13.92 squared is this a milliamp output of 73.5 MA. That's our magnitude, the first number here. 73.5. And then our phase angle is that inverse tangent equation. And to the -1 of B over A, so that's 13.92 over 72.2. That'll give us our phase angle. So function inverse tangent 13.92 divided by 72.2. Make sure you're in degrees for this one, because if you're in radians, it's going to calculate incorrectly. So make sure your calculator's in degrees. 10.9 is what we get for that. 10.9 degrees. We'll plug that in for our final answer. And we'll verify at the bottom. All right. That's what they wanted for that one. So let us know if you have any questions. Watch out for those negatives in there because of this backwards equation right here. That's going to get you an incorrect answer if you miss that negative or you add the negative when it's not supposed to be there.